All right, this is Geometry B Unit 3, Lesson 2, Biconditionals and Definitions. So we're going to examine biconditionals today, but that involves some review of what we talked about last unit or last lesson. We have this idea called a conditional statement. Conditional statement. Which consists of two parts. An if part and a then part. If I have a Dalmatian, then I have a dog, right? The if part, Dalmatian, is called the hypothesis. It's the condition that is met. The then part is called the conclusion. It is the result. Okay? And graphically, it is demonstrated or written this way. If this is statement A and this is statement B, this is written A implies B. Dalmatian implies dog. If you have a Dalmatian, then you have a dog. And I have a dog barking outside my window. Right? And each statement has a truth value. This statement has a truth value of true, because a Dalmatian is a type of dog, and we can demonstrate that by a Venn diagram. Dalmatian is one group, the group of dogs. There's a group of dogs known as Dalmatians, and there's a larger group known as dogs, right, of which Dalmatian is a part. And there are other dog groups in dogs, like German Shepherds and Huskies and Chihuahuas and all these different dog breeds, right? So Dalmatians, if you're in the inner circle, you're certainly in the bigger circle. If small circle, then large circle is the way it works. Okay? But if I switch things around and write the converse of the statement, and switch things around, then things change quite a bit, right? So if I write this, if I have a dog, then I have a Dalmatian. That has, if I have a dog, then I have a Dalmatian, that has a truth value of false. That is false. Okay? And the symbolism for that is B implies A. False. B implies A. Notice how the order has switched. A implies B became B implies A. And it's false because I can think of a counterexample, which would be a husky. A husky is a dog. That makes that true, but it is not a Dalmatian. That makes that false. So this is what's known as a counterexample. And notice Dalmatian is a small group belonging to a bigger group, dog. I cannot say if I'm in the bigger group, I'm in the small group. So it doesn't go from small to large, large to small, right? But there are some statements that are reversible. This one is not, but there are some statements that are reversible. For example, if x is even, let's take this, x is even. Okay, if x is even, well, I'm going to take that as my hypothesis. If x is even, then x divides by 2 evenly. Divides by 2 evenly. Okay? If x is even, does it divide by 2 evenly? Yes. Right? If a number divides by 2 evenly, is it even? And the answer is yes. Okay? This flows both directions. Right? So I can write two conditional statements. If x is even, then it divides by 2 evenly. And if it divides by 2, if x divides by 2 evenly, then it is even. Okay, so x, or this diagramming would be A implies B. Let's do this way. A implies B. This would be B implies A. We can shorten this all to a single statement called a biconditional. Biconditional. We can shorten it to this statement. We can say x is even if and only if it divides by 2 evenly. Okay? That phrase, if and only if, is equivalent to our double arrow. It goes both directions, right? And so for the future reference, we can shorten that. Mathematicians recognize this. This is not an English word, but it is a word in math proofs. IFF. If with a double F. If stands for if and only if. Okay, so x is even, IFF, if and only if. It divides by 2 evenly. And that is a way to write both statements. If x is even, it divides by 2. If x divides by 2, then it is even. That's a biconditional. And that is a good explanation of a definition. Definitions must be biconditionals. They must work forward and backwards. For example, a shape is a square if it has 4 sides and 4 right angles. If a shape has 4 sides and 4 right angles, then it is a square. So we would say the definition of square is a shape with 4 sides and 4 right angles, and 4 congruent sides. Forgot that. 4 congruent sides and 4 right angles. Okay. All right. So that is our definition, and that definition works both forward and backwards. Now, graphing-wise here's what this basically comes to. This comes to x being even. Let's move this here, right? So Venn diagram-wise, it looks like this. It looks like x is even, all the sets of even numbers. Oh, come on. I've messed it up here. All right. So we have all the sets of even numbers, and we all have all the set of numbers that divide by 2, right? So even and divide by 2. But the way the Venn diagram works is one is superimposed on the other. They exactly fit into each other. So we can move this over, and they are the same set. They overlap each other perfectly. Okay, so that's kind of basically the idea of a biconditional in the Venn diagrams. It works both ways. You're talking about the same set. The same set is satisfied by both requirements. All right, so hopefully that helps.